Polyprotic acids, like sulfurous acid, H2SO3, have more than one ionizable H. We see two equations that relate to equilibrium constants. The first one has one H popping off, and there's a certain equilibrium constant that relates to that. And then the second equation shows the second H popping off, and there's a different equilibrium constant that applies for that case. If you look at the magnitudes of the Ka values, if you just look at the power of 10, the first one in this case is 10 to the negative second, and the second one is 10 to the negative eighth. That's 1,000,000 times different, which is quite a bit. And the reason that the second Ka value is so much smaller is because it's harder to remove additional protons. Kind of like the bully at lunch in grade school. It was tater tot day, and the bully might come by and grab one of your tater tots. That first tater tot was fairly easy for him to steal because you weren't expecting it. The second tater tot would be much harder because now you're on to him. Not that it can't be done, but it's a lot tougher. In the same way, losing one proton is one thing. Losing a second proton is much more difficult. Now here's the nice thing about polyprotic acids. Usually Ka2 is at least 1,000 times smaller than Ka1. In such cases, one can calculate the hydrogen ion concentration and the pH based only on Ka1. That is, ignore Ka2 and pretend you have a monoprotic acid. Let's show you an example. Find the pH of a 0.0037 molar carbonic acid solution. Carbonic acid has two ionizable protons. You can see that we have two Ka values. Here's the first H popping off, and let's write an ice expression where we're going to combine the initial, the change, and then we're going to write just the at equilibrium line. 0.0037, which is the initial, then that amount will go down, some amount x, and with the hydrogen ion, and this one here on the right is called the bicarbonate ion, both of them start at 0 and then go up by some amount x. Substituting the values into the equilibrium constant expression, there's our Ka1 value. There we have products, x times x, and there we have the reactant value. If we use the quadratic formula to solve that, x comes out to be 3.97 times 10 to the negative fifth molar, and then of course we can find the pH by taking the negative logarithm of that. If instead we use the shortcut, which we talked about in an earlier lesson, which says that x is very small, so in the denominator 0.0037 minus something very, very small is essentially 0.0037. That's a lot easier to solve than using the quadratic formula, and if you do solve that, you'll get this value, 3.99 times 10 to the negative fifth, which you can see is very, very close to the value you would get from the quadratic formula. In fact, to 2 places past the decimal, the pH is exactly the same. This is where the pH stands after we've lost one proton. We're going to go through on the next slide what additional effect takes place when we lose the second proton. After what went on the previous slide, the hydrogen ion and the bicarbonate ion concentrations after the first ionization are right here, 3.97 times 10 to the negative fifth. I'll go ahead and use the value that you get from the quadratic formula and not the shortcut value, but it really doesn't make any difference. Let's now show what happens when, for some of these, a second proton is removed. Now this one is a little bit more of a complex expression because we need to pick up from the point at which we've already lost one proton, which means that the initial concentration for this case, for the bicarbonate, is 3.97 times 10 to the negative fifth, and that amount will go down some bit. The hydrogen ion concentration initially is also 3.97 times 10 to the negative fifth. That amount will go up somewhat, and we will then produce, for the first time, some carbonate ion. So instead of X this time, I'm going to use Y. We need to use Ka2 here, which is 5.6 times 10 to the negative 11th. So this is much smaller than the Ka1 value. You can see we've done products in the numerator, reactants in the denominator. You can see that this looks like it's going to be a lot of work to solve, and it is. We've simplified it here, and if you solve that for Y, feel free to do it if you want, or you could just trust me. The additional concentration of H that will be produced due to some of the second protons popping off is right here, 5.6 times 10 to the negative 11th molar. When we assumed that only one proton popped off, we got 3.97 times 10 to the negative fifth molar. Those are 1,000,000 times different. In other words, this number that we computed fairly easily by assuming only one proton coming off, and in fact we could use a shortcut for that too, that's 1,000,000 times more than what we get if we do all this work to find out how much additional H plus is popped off. In other words, the pH is still going to be 4.40 and nothing will have changed. So if you have a, in this case, let's say diprotic acid that's weak, if you assume that just the first proton has been ionized, you're pretty much good to go.